Hardware to Save a Planet explores the technical innovations that are giving us hope in the fight against climate change. Each episode focuses on a specific climate challenge and explores an emerging physical technology solution with the person bringing it into reality. I'm your host, Dylan Garrett. Welcome to Hardware to Save a Planet. I'm excited to be talking today with Dr. Laura Lammers, founder and CEO of Travertine, about a novel process for generating carbon-negative sulfuric acid that uses sulfate waste from industry as an input. This is exciting because it tackles a couple of big climate challenges. One, carbon dioxide removal, which, as we've talked on the show before, needs to be happening at gigaton scales in order to meet our climate goals. The other is that sulfuric acid is the world's most produced chemical, and it's critical to supporting the industries that are making our transition to renewable energy possible. It's used for lithium extraction, for example, which is skyrocketing with battery manufacturing. So if we could produce sulfuric acid in a sustainable way while simultaneously storing CO2, it would be a major double win for the planet. To introduce Laura quickly, she did her Ph.D. at UC Berkeley and has spent many years doing fundamental research to understand the Earth's natural processes that regulate carbon cycling. So she was studying carbon mineralization way before it was cool. In January this year, she made the jump from academia to start Travertine with the goal of turning her research into scalable impact on climate change. So welcome, Laura. I'm really excited to have you on the show. Thanks for joining us.
Thanks, Dylan. I'm really excited to be here. And I just want to say that carbonate mineralization has actually always been cool. I was just the one who realized it sooner than most.
Yeah, you discovered the coolness. Okay, well, understood. Good point. Cool. So yeah, I'm excited to talk about it because I also find it to be very cool. Before we get into Travertine, I'd actually love to just learn more about your background. You're on this ambitious mission. What events in your life led you down this path?
Yeah, I think it's just been a series of events that have all kind of led in the same direction. So when I was a kid, I was always interested in the natural environment and learned about environmental challenges. I grew up in Houston, Texas, and so was kind of steeped in this fossil energy culture where my parents were kind of big environmentalists. And so was always kind of thinking about environmental problem solving. And so I decided to go to Dartmouth College for my bachelor's because they had a really, really good earth science program. And so got into environmental chemistry at Dartmouth and started working in a lab pretty early on. At that point, I was looking at kind of arsenic in soils and arsenic remediation, but interested again in kind of how we can affect change in the environment with engineering solutions. And then in my PhD, I went to work with Don DePaulo at UC Berkeley. And it just so happened that at that time, he was leading or just started to lead a center, one of the first centers on geologic carbon dioxide sequestration in the subsurface and understanding what's going to happen to the CO2 that we put underground. And that got me into the field of carbonate mineralization. So I did my dissertation in kind of fundamental chemistry of carbonate formation and really have ever since been working on carbonate mineralization, what controls the rates of formation, what controls in the deep oceans formation and recrystallization of these things. And so that's what got me into carbonates in particular in the carbon cycle. After PhD, I went to a brief postdoc and was just kind of feeling this gap between academia and application. So I went briefly into environmental consulting, but then decided to come back to academia when I got a position at UC Berkeley. And so in my lab at Cal, then continuing this research stream in carbonate mineralization, but also getting into a little bit more applied selective element extraction. And so this is kind of what all of these streams of research coalesced into what now is Travertine. Yeah.
Awesome. I think you're one of only two CEOs I've talked with who's made that switch from academia to running a company and everything that comes along with that. What's something you learned about the differences that you didn't expect?
I think maybe one of the things that was unexpected is, at least at this scale, how similar it is to running a research group in a sense, because when you're a PI of a lab group, I spent really probably the majority of my time fundraising, right? So I was always writing grants, interacting with grant organizations, administering projects. So there's a lot of that administration and business aspect of academia that people don't really think about. All you think about is kind of doing the science. And so there's a lot more of that running a small business to academia, maybe than people appreciate. But layered on top of that, of course, is teaching and lots of service. And so coming out of academia and starting this company has been really a breath of fresh air, because really I get to focus in depth on one thing that I think is really important, I'm excited and passionate about, and I'm not distracted by a lot of other things that I also think are important, but kind of prevent me from making a lot of progress in one specific goal. And so I think maybe the most surprising thing is how similar it is, at least at this stage. I think that'll change as we grow, but right now it's really just been extremely fun. Yeah.
Cool. I did not expect that answer, but that makes a lot of sense. Could you start by kind of just giving us a high level description of what it is Travertine is doing?
So Travertine is working to solve two big problems. So the first is sulfuric acid production. So sulfuric acid, as you said in the introduction, is the world's most used inorganic chemical. And the way that we produce it now is by basically burning a byproduct of fossil energy manufacturing. And so the way that we produce sulfuric acid and the way we use it is not clean, in the sense that the sulfuric acid we use then generates massive sulfate wastes that are environmentally hazardous in many contexts. And so what we're trying to do is eliminate that waste stream and upcycle sulfuric acid. And then at the same time, we need to do carbon dioxide removal. And so Travertine's process has basically come up with a way to efficiently upcycle sulfuric acid while sequestering carbon dioxide permanently from the atmosphere and carbonate minerals. And we can do these things together through water electrolysis, which allows you to produce equal quantities of acid and base. And so we can take a sulfate waste feed, like, for example, a phosphogypsum, which is a waste product of fertilizer manufacturing. So we take this sulfate waste feed, we put that into our precipitation reactor, where we react that with carbon dioxide from the air and base out of a water electrolyzer to produce carbonate minerals. And so that's where the CO2 goes to permanent sequestration in a carbonate mineral, kind of like the way that the Earth sequesters CO2. At the same time, we're taking the sulfate, we're liberating that from the waste stream, and then we're turning that back into sulfuric acid. And so we can take a waste feed and turn it into something good, which is a permanent carbon sequestration, maybe even something we could use as a green cement product down the road, while at the same time upcycling that sulfuric acid, making those kind of linear resource extraction techniques that we're really good at doing as humans into more cyclic ones that hopefully we're shifting towards now in this century.
So to understand the problem a little bit more, so is sulfuric acid production itself harmful to the environment, or is it more about the waste produced in using it?
I wouldn't say that sulfuric acid production itself is harmful to the environment. It's a highly industrialized process. We're doing it all over the globe. This is not problematic in itself. I think the issue is that, one, the feedstock for sulfuric acid production, elemental sulfur, is a waste product of fossil energy manufacturing. So you're kind of subsidizing fossil energy production by purchasing sulfur. And then the second thing, and probably more important thing, is that in conventional sulfuric acid, you're just generating new acidity and then generating new sulfate. And so this sulfate has to go somewhere. Either it goes into a big pile of solids like calcium sulfate salts, or it's getting kind of diluted into surface waters. And so there are environmental impacts of discharging this much sulfate into the surface environment. And so it makes more sense in some ways, if it's possible and efficient, to take that sulfate and turn it back into sulfuric acid.
When we talked before this, you'd shown me a picture of a mountain of sulfate waste, which is pretty impactful to see just kind of how much of this stuff is sitting around, not being used. And it sounds like maybe leaching into the water and causing issues there and stuff.
It's truly staggering, the scale of these waste products. So in the most sulfuric acid in the world right now is used to produce phosphorus fertilizers, which are absolutely critical for feeding the world. We can't get around producing phosphorus fertilizers for a lot of difficult chemical reasons that I don't want to get into now. But when you produce phosphorus fertilizers, you're taking this geologic feedstock called rock phosphorus and reacting it with this sulfuric acid, and it generates phosphogypsum. And every year we produce hundreds of millions of tons of phosphogypsum. And you can imagine that multiplied by 70 years of making phosphorus fertilizer in this way, there are many billions of tons of this stuff piled up all over the globe. You can see it from space. And the issue is that this PG is slightly radioactive. And so you can't really beneficially reuse it, right? And so we're really running out of space to store it. And at least in the United States, it's almost impossible to permit a new phosphorus production plant because the EPA won't allow production of more phosphogypsum.
I'm kind of wondering if there's what that means for our ability to kind of continue, if we don't find a way to use this waste to continue producing fertilizer or extracting these elements and that kind of thing.
Yeah, I don't think the US really has a long-term plan other than let's buy it from somewhere else where they're less restrictive in their environmental regulations, which I don't think is a good long-term solution. I'm all for let's manufacture these chemicals here in the most clean way possible.
Mm-hmm. Let's just for a second take the carbon dioxide removal part of your solution off the table. It sounds like even without that, there's a big benefit here in that you're finding a use for this waste to produce more sulfuric acid. Is that the right way to think about it?
I mean, yeah, I think one of the more surprising things coming out of the lab bench and talking to potential customers for our process is that they're most interested in the sulfate waste abatement side of things rather than the carbon dioxide removal side of things, because waste management is very expensive for companies. And so that's actually been a bigger selling point to our commercial customers who would buy sulfuric acid, for example, than the carbon sequestration side.
And on the carbon sequestration side, how does it compare? How should we look at it in comparison with other CDR technologies?
Yeah, so great question. So compared to other carbon dioxide removal technologies writ large, most technologies are focused on separating CO2, generating a compressed carbon dioxide stream. And so the difference for us is that we're kind of generating chemical products at ex situ, so on Earth's surface, that could then be used for other applications. And so I think our main differentiator is that we're trying to beneficially use all of the products of carbon dioxide removal rather than simply just storing the CO2 underground.
Let's talk about the business a little bit. You mentioned your customers a second ago. So what exactly will you be selling to them? And can you describe who those customers are?
Yeah, I would say at this point, we have a couple different flavors of customers. The main customers early on are going to be today's biggest users of sulfuric acid. And so fertilizer companies, for example, who are producing the phosphogypsum stacks would be a great customer because not only can they supply the phosphogypsum waste, which is a feedstock for our process, but they can purchase the sulfuric acid that we produce, as well as our other co-products. So another co-product of our process, I hadn't mentioned this before, is green hydrogen, because we're making acid and base electrolytically, meaning we're splitting water, which means you produce hydrogen in that process. And we're doing it in an electrical way. So it's green hydrogen. And so they can take our sulfuric acid, they could conceivably take our hydrogen for their ammonia production processes, and they can basically use our carbonate products. And so I think all of these things together make that a very appealing direction from a business perspective. Another important customer is the mining industry. And so there are many, many different mining processes that require the use of sulfuric acid. These include hydrometallurgical extractions, where you have kind of a dilute sulfuric acid leach. And this would be typical of like a lithium extraction from a clay stone or some kind of unconventional deposit. And so mining companies are also potentially great customers in the sense that they can use our sulfuric acid products. And many of them have kind of top-down corporate mandates to reduce or eliminate carbon emissions in their production processes. And so that's another kind of win for them. Another issue is that in a given project that's being planned for a mine, all of those undergo environmental review. And in some cases, waste generation is the difference between a mine getting permitted and not. And so if they can come to a permitting agency with a process that eliminates this massive waste stream, I mean, most of these mines are going to be producing thousands of tons of sulfate waste a day, which again, it's not that environmentally hazardous necessarily, but it is a huge waste stream where if you have a water limited ecosystem, it might be hard to get rid of that. And so it might mean the difference between a mine effectively getting permitted and not.
You mentioned the kind of corporate environmental mandates. What's behind that? Is that being driven by regulation or kind of pressure from other parts of the supply chain or something like that?
I sure wish it were being driven by regulation, but at this point, it seems that it's actually on some level voluntary and really kind of a choice that I think is driven by pressure from customers wanting companies to be producing their critical elements in an environmentally sustainable way, right? But I think a lot of these mandates are really top down. It's coming from the CEO saying we need to cut carbon emissions by 50% by 2030. And that means that these companies are starting to kind of price carbon internally, which is really useful when they're kind of evaluating potential technologies they can use in their mining processes.
When they look at it kind of holistically, it sounds like maybe there is a financial kind of incentive to do it this way. Is that right?
I think there are a lot of incentives in terms of waste abatement and internal pricing of carbon credits, but also, there are other government programs now through the Inflation Reduction Act that have real prices on carbon where, we could sell those credits separately from selling these products to the customer. So for us, from a business perspective, we're trying to understand whether it makes sense to be retiring these credits internally to the process or selling them separately on an open market. And so that's something that we're kind of thinking through now.
Yeah, I was going to ask about the Inflation Reduction Act. Can you say a little bit more about how that's impacting things for you?
I mean, I think in a number of very positive ways. So there are direct tax credits that we could benefit from. So there's a credit for carbon dioxide removal and sequestration. That's that 45Q credit. And then there are also green hydrogen credits, which can't be used together with the carbon sequestration credits, but there may be cases in which we're doing more abatement than sequestration and then could take advantage of that green hydrogen credit instead. And so that's wonderful. And then there's also the tax credits going to producers of critical elements that is really encouraging domestic production, critical elements like nickel, lithium, cobalt, platinum group metals, all these different materials that are going to be essential for renewable energy hard tech, right? So this is good for us in the sense that these companies are going to be, quote unquote, onshoring, coming back to the US, meaning they're subject to the stringent environmental regulations of the United States. And so they have more pressure to manage waste more responsibly than they would in a lot of places internationally where mining is done. Yeah.
You told me when we first met that you see a path to gigaton scale carbon dioxide removal. What's required to get there? What does that look like?
I think this is true.
That's a lot.
I think this is true for all of these carbon dioxide removal companies, but just incredibly massive infrastructure, right? Just big chemical plants, right? I mean, you've seen the pictures probably of these air contactors that are being built or designed in the future. And these are tens of thousands of tons per year, not millions of tons per year. And so these are just going to be really, really big projects. And so it's a lot of really big plants. And so I think that's what the future of carbon dioxide removal looks like, is a lot of big chemical plants, honestly. And that might not be what people envision when they're thinking a clean, green future, but I think that's the reality of it.
And those would be, in your case, those would be located on site with these big mining operations or fertilizer production operations. Is that right?
Yeah, for us, it would be co-locating with sites where there's already industrial impacts, fertilizer producers. And so the footprint wouldn't necessarily be much bigger than what they've already got going. But in the context of mining, we'd be co-locating with where they're actually processing the materials, not necessarily where they're mining. In a lot of cases, where they actually extract the ore is not where the processing is taking place.
And in terms of scale, you mentioned, I think, hundreds of millions of tons of the sulfate waste a year we're producing. And is that sufficient to get to gigaton CDR removal or CDR?
Good question. So right now, let's think of this in terms of global sulfuric acid demand now and projected for 2040. So right now, it's about 250 million tons per year. By our process, we sequester about half a ton of carbon dioxide per ton of sulfuric acid produced. And so today, if we replace all conventional sulfuric acid production, the wave of a wand, then we could sequester per year around less than 100 million tons of carbon dioxide. By 2040, the projection is we'll be using more like 400 million tons of sulfuric acid a year, and that's getting into like peak sulfur territory where we might be short on sulfur. In that case, we'd be sequestering something like 200 million tons per year of carbon dioxide. So to get to gigaton scale carbon dioxide removal by our process, we have a couple of different options. So the first is enhanced weathering of mine tailings, where we basically take waste materials from mining and be constantly producing and recycling sulfuric acid. And if we process all of the what we think of as being suitable waste materials from mines, meaning ultramafic rocks, then there's a pathway to gigaton scale carbon dioxide removal. We're going to be producing enough of that material. But it means really we're producing a lot more sulfuric acid than is used globally today. We're just using it right away, if that makes sense. It's not going anywhere. It's just being used and recycled right away. Another option that we have actually is to kind of cycle our process a la carbon engineering or Heirloom, for example, where we produce a carbonate and then we convert it back into a pure CO2 stream. And so that's another option to get to very large scale carbon dioxide removal. But that starts to look a lot more like quote unquote conventional direct air capture and sequestration, where we're basically not producing a useful sulfuric acid product. We're not producing a useful carbonate product. We're simply reacting our acid and carbonate again to get pure CO2. And so that's another way to get to much larger scale carbon dioxide removal with our process.
Interesting. So you'd be extracting the CO2 again from the carbonate minerals.
Exactly. What it does is essentially concentrates the CO2 so that you can actually pressurize it to supercritical and then inject it underground.
Mm-hmm. And where are the biggest, just thinking about the technology, where are the biggest kind of innovations in what you're doing? What hasn't been done before?
Yeah. So what's kind of new about our approach to this process is essentially the way that we are marrying this water electrolysis process with precipitation process. So historically, people have kind of upcycled sulfate waste by processes like bipolar membrane electrodialysis, which is a salt splitting process, which kind of takes a sodium sulfate feed or some other sulfate feed and then splits it out into acid and base. And you need kind of a complicated ED system to do that. What we're doing kind of couples the water electrolyzer with the precipitation reactor in this continuous flow configuration so that we basically consume all of the base that we produce at the same rate that we make it, which means that we can maintain very kind of gentle chemical conditions in the electrolyzer. And that means that we can use off-the-shelf readily available materials for our water electrolyzer. And so at this point, our process combines this water electrolyzer and a precipitation reactor. And so, of course, there's other stuff in there, but that's just kind of high level, the two main subunit operations. The water electrolyzer is a combination, it's kind of a unique combination of an acid electrolyzer and an alkaline electrolyzer. And these have separately been industrialized, but not really together in the way that we're using it. And so because of this, we can actually use the electrodes that have been developed and commercialized for those different electrolysis processes. One thing kind of longer term that we would like to see is improvements to the membranes. And so because, again, we're doing this kind of gentle, we're using these kind of gentle conditions in the cathode side of the electrolyzer, we're able to maintain our membranes for long periods of time. But we'd love to see more kind of ion selective membranes being developed. We'd love to see membranes that are more tolerant to high base concentrations so that we can get a little bit more creative about the chemistry of the system. But right now, there's plenty of industrial components that we can use in our process available to us already. There's certainly room for improvement down the road, though.
And is that the kind of thing you would tackle at Travertine, developing those new membranes, or something you're hoping comes from other parts of the industry?
Yeah, I mean, I don't know if I see us necessarily as membrane production and R&D. I think we would definitely enter into partnerships with membrane producers and suppliers because there are ways in which membrane chemistry can be adjusted to be more relevant to a specific process. And so we would look to partner with membrane producers to kind of co-develop materials that would be most adept at the chemistry that we're trying to accomplish in our process.
What are some of the big hardware challenges you expect as you scale up, or maybe that you've already had to tackle?
Yeah, I mean, I think scaling the electrolyzer, maintaining efficiencies and maintaining operations and kind of complicated feed solutions is going to be the biggest hardware challenge that we face. So conventionally, people try to avoid completely introducing divalent ions like magnesium and calcium into your electrolyzer because they can form scales, which can deposit on the cathode and on the membrane, and then you end up with high voltages and low energy efficiencies. And so part of our kind of our learnings and our kind of trade secrets, if you will, is around maintaining low energy intensities, so high energy efficiencies of acid production in the presence of these dissolved salts. And it's really just a matter of kind of managing the formation of scalants in the electrolyzer. And so as far as like hardware, where we're innovating, it's operating conditions of the electrolyzer, but also component selection. And we have the advantage, again, of being able to select from components that are already used widely in industrialized alkaline and acid electrolysis. But it's basically making kind of a novel combination of these materials to develop our electrolyzer.
As you put the whole thing together, are you worried about, is total energy budget something to be concerned about? Just, I know that's a big conversation in CDR.
Energy budget is everything.
Yeah.
Yeah. Energy is everything, right? Because for any given carbon dioxide removal process or any chemical production process is what's the cost? And for us, water electrolysis is by far the driver of operational cost because water electrolysis takes a lot of electricity. And so what we need to make sure is that we can produce our acid and base with very high, what's called Faraday efficiency, just very high efficiency, so that all the energy you put into the electrolyzer is actually going to make acid and base rather than kind of having quote unquote Faraday losses, which is just an inefficiency in your system, making heat very expensively, pretty much. And so energy is everything. And this is also another important part of kind of strategizing around first citing our first commercial operations is we need renewable electricity and we want to be sourcing it from places with excess renewable electricity. We do not want to be taking from a grid where if we weren't using the electricity, then it's a coal power plant making up the balance of the grid, right? And so this kind of narrows down geographically locations that we can operate. And there are certain sites where there might be a potential energy resource that's otherwise untapped that we can tap into that currently can't be exported to the grid. And so that looks really great because then we can do carbon dioxide removal and sequestration using an energy resource that otherwise wouldn't be used.
Like what's an example of that?
Well, so if you locally have, for example, a geothermal resource that can't be exported to the grid, then you could use that energy to produce electricity for some extractive process where it couldn't be exported otherwise, which is why, for example, all this DAC is happening in Iceland, right? It's all this geothermal electricity that's way in excess of the needs of the Icelandic people, right?
What about using your hydrogen?
Yeah, absolutely. So we will definitely use our hydrogen, but we can't get back all of the energy we need from the hydrogen, right? It's a fraction of the energy we need, but that could help us operationally in places if we don't have consistent energy supply. If we're using solar electricity, for example, then we could store our hydrogen for use at night. And then hydrogen also could be, depending on siting and whether or not we can actually export it to a market efficiently, we could compress it and sell it. And a lot of times that makes more sense economically than actually using it where we're producing it.
So what do you think Travertine looks like at steady state, let's say, whenever that is, 10, 20 years out?
Yeah, I think it looks like we're operating a lot of large commercial plants in tandem with critical element extraction operations, but also in tandem with fertilizer production operations. And hopefully these plants will last a long time. And that's kind of the goal, right? And so we'll be hopefully a steady state of kind of commissioning new plants and then developing new projects for different applications. And that's kind of what it looks like to me. But a lot of big industrial facilities, which is something that I had never imagined being a part of as an academic, certainly.
Mm-hmm. What other problems might you tackle that are either on your roadmap or you would put on your roadmap if you had kind of more time and resources?
I've always been kind of interested in kind of closing the loop on nutrient sustainability. And so one thing that I would love to integrate more in the longer term is more sustainable production of fertilizers. So not just carbon negative, but how can we use nutrients that we recover from wastewater? So one of my PhD students, Luis Anaya, now is working on struvite, which is a mineral that you can grow out of wastewater that pulls out all the phosphorus and it also pulls out ammonium. And so how do we recover struvite in a way that makes it possible to close the loop to the extent possible on phosphorus budgets, because phosphorus is really tricky and I don't want to go into it too much now, but we want to recover as much as we possibly can from waste streams and reuse it rather than simply extracting it from raw earth materials. And so getting more into sustainable nutrient recovery and just expanding this sustainable chemistry focus of our company.
A few closing questions. I like to ask everybody these. What is your perspective on the future of our planet? How optimistic or pessimistic are you, and why?
So I mentioned this to you, but maybe folks listening would know this is I am a mother of 3 young boys, and you can't be a parent of 3 children and not be, to some extent, an optimist, right? I believe that we are capable of solving this challenge if we essentially value the environment appropriately and we put penalties. I don't know if we want to say penalize things, but we accurately account for the costs of environmental degradation, right? Which is what we're starting to do by pricing carbon emissions and carbon contamination of the atmosphere. And so personally, I'm an optimist because I believe that the technologies that we need to get out of this climate crisis are things that we already have on deck. There's going to be improvements, obviously, and improvements in efficiency, but we can solve this now if we price carbon emissions appropriately. And so from that perspective, I'm an optimist. I mean, we already move Earth materials at a scale that's relevant to carbon sequestration at the scale that we need to do it. And so I really do believe that we can solve this. And I think this is a message that's important for students to hear also, because I feel like recently, the last couple of years, people have been feeling a little bit helpless. I truly believe that we can solve this. We just need to be doing it at this point. All hands on deck.
I love hearing that, especially as a soon-to-be father of 3 myself.
Great.
Yeah, no, thanks for saying that. Who's one other person or company doing something to address climate change right now that's inspiring you?
Oh man, there are so many amazing examples, but I think I want to say I'm most inspired by my recent Ph.D. student graduates who have gone into different climate tech companies. So one of them, Elliot Chang, went to co-found ION, which is another Stripe portfolio company, which is trying to do enhanced weathering agricultural soils. And then my other student, Jennifer Mills, who went to work at Heirloom. And I was inspired by my students and inspired by them to kind of take the leap out of academia and back in industry, because they showed me that it was possible to, and that their skills that we've been developing, so laboriously over so many years are useful to help solve this problem right now.
What advice do you have for someone not working in climate tech today who wants to do something to help?
I think I heard this on the radio somewhere, but it really resonated with me. I would say in the Venn diagram of what you love to do and what you think the world needs right now, try to find that overlap to the extent possible and use your skills in a way that you think is beneficial to the earth. I mean, the climate crisis is one of the problems that we're facing. There are so many other things, right? And so just finding your sweet spot, what you feel like you're good at and what you love to do, definitely has an outlet and something the world needs. It's just a matter of finding that overlap, I think. It's worth investing some time in. Do a little soul searching.
I love it. Yeah. Laura, thank you very much. It's been really fun to talk with you. I've learned a lot and definitely have some brushing up to do on my chemistry, but I really appreciate it. It's been really fun and I'm inspired by what you're doing.
Thanks, Dylan. I really appreciate you putting the show on and trying to educate folks, and just the opportunity to be here. It's a big honor. So thanks a lot.
Hardware to Save a Planet is brought to you by Synapse. To find out more about us and how we develop hardware solutions for the world's most ambitious companies, head to synapse.com. And then make sure to search for Hardware to Save a Planet in Apple Podcasts, Spotify, and Google Podcasts, or anywhere you like to listen. Make sure to click subscribe so you don't miss any future episodes. On behalf of the team here at Synapse, thanks for listening.